Hey everybody, this is my lesson about the mathematics covered in Chapter 1, Chemistry and Measurement, that I did not cover in a lecture in order to make up for the time we lost in the first week of class that was canceled due to COVID issues. All right, so here's just the chapter outline. We'll be doing measurement and significant figures. We'll be doing units and dimensional analysis as well. All right, so section 5 is measurement and significant figures. When we have numbers that we're measuring as scientists, chemists, physicists, engineers, whatever, there's many ways to represent magnitude, numbers, quantities, two of which here will be the standard notation and scientific notation. Standard notation would be numbers like 100, maybe 1,000, or we could have decimals in standard notation like 0.1 or 1/10, 0.025, etc. That would be numbers in standard notation. Scientific notation, also known as exponential notation, though, is utilized in order to make very large or very small numbers easier to read and take up less space. So, for example, we have a number in chemistry that is used very frequently called Avogadro's number. And it is 6.02, well, let me go back. It is 602 sextillion, 200 quintillion, all right, that's a very long number. But I don't want to write all that. That's standard notation. It takes a long time to do that. There are a lot of place values there that are almost irrelevant. So instead, we can write it in scientific notation. Now, in scientific notation, this would be 6.022 times 10 to the 23rd. It's a lot smaller, makes a lot more sense when looking at it. So, for example, we have this exponential part here, the 23. We've got the base of that, the power of 10, or the base 10 to the power of 23. What that tells you is that the decimal, which would be placed here, we leave it off normally in standard notation if it's unnecessary. It's a phantom decimal. The 10 to the 23rd tells us that this decimal is moving 1, 2, 3, 6, 9, 12, 15, 18, 21, 22, and 23 times to the left in order to convert it from standard to the scientific notation. Another way of looking at it is how many place values come to the right of that first digit right here, the 6. How many come to the right of it before the decimal right there? If we count those up, let me change the color here. Let's use white, I guess. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15, 18, 21, 22, and 23. And again, the exponential part up there is 23, 10 to the 23rd. And so it's telling you the magnitude of that number, but it's taking up a lot less space. Another example would be like the charge of an electron, which is 1.602 times 10 to the negative 19th coulombs. We'll leave out the units for now. Now this, again, we saw in class is in the scientific notation. So in the previous example with Avogadro's number, I wrote it in standard notation, showed you how to convert it to scientific notation. It's just counting these number of place values to equal the exponential there. And it's always times 10 in science, base 10 to some power. Now here we have scientific notation. If we're converting that to the standard notation, we can take the decimal from 1.602 and move it. Now, in the previous one, we moved it from right to left when the exponent was bigger than 0 or positive. And for this, we're going to move it to the left as well. But the reason is we're going from scientific to standard, whereas in the previous one, we went from standard to scientific. So we're going to move the decimal 19 times to the left. Now, if we move it once, we would have the decimal right there. And that would be 0.1602. So you'd have this, all right? But we're going to do this another 18 times. So we need to create all of these zeros. So we moved it once there. Now 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. All right, let me make sure I have this correct here. 4, 5, 6, 7, 8, 9, 10. And I got to do it, okay, a 19th time. It was another 18, but I only did it 17. All right, so now what you need to do when you've done that is place a 0, these phantom zeros, in every swoop. There's a lot of them. No one would want to write this decimal number in standard notation because there's just so much empty, useless space here. All of these unnecessary zeros. And then so you get to the last place, and the decimal is going to be right there, and your last phantom 0 goes there. Now, if we count up these zeros, you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and lo and behold, 19 zeros. So instead of doing the swoops and putting them in, and sometimes your swoops can get lazy, and not that, I'm assuming you do that, but people do it, myself included, and sometimes they just overlap and you miss one and miscount and everything. I would just say you have a number like this, you write in your 1602, and then put in 19 zeros to the left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Then put your decimal in, always after the first 0. And there you go. In standard notation, 1.602 times 10 to the negative 19th coulombs is this value there. All right. So if you're going from standard to scientific notation, if it's a whole number, you're moving the decimal to the left. And how many times you have to do that, or how many place values are to the right of the first number, is the exponential value here, 10 to the 23rd in that case. If we start off with a decimal, let's just give it 0.025. In this case, now the number is less than 1. So what we would do is we would move it twice to the right, which means this is 2.5 times 10 to the negative second. But you could also just say how many zeros were to the left of the 2. There were 2 of them, and that's why it's negative 2. For scientific notation to standard, again, it's how many, is how many zeros there are. If it's a negative exponent, the zeros go to the left of the first number. If it's a positive exponent, let's say it's like 300 and, or let me not do that, 5.89 times 10 to the 4th, this is telling me that there's 4 place values after that 5. So 5, and then we've got 2 here, so we need 2 more. It become 589 and then 0, 0. Put in your comma after that if you want, so it's 58,900. So the key takeaway here for scientific notation is that there is always, no exceptions to this, a single number followed by a decimal and then all necessary digits. And so, like, what I'm talking about there would be the 6.022 part. That gives you the value of whatever the measurement will be, and then the exponential part will give you the magnitude. And so if I'm going to name it, this portion here is called the coefficient. So let me put that in. Okay, and then the coefficient is going to be followed by the exponential part. Let me erase some of this stuff off of there so it's less messy. And so this is going to give the magnitude of the number. In base 10. All right, so again, if I put 3 times 10 to the first, this would be 30, because it's really 3 times 10. If you have 3 times 10 squared, it would be 3 times 100, essentially. You know, actually, let me fix that. Let me show it all out a little bit more. So it becomes 3 times 10, because 10 to the first is just 10. So that's 30. If it's 3 times 10 to the second, it's 3 times 10 times 10, which is 3 times 100, or 300. Those are positive exponents. Just as a side note, if you have 10 to the 0 power, this is 3 times 1, because any number to the power of 0 is 1. And so that would be 3. If you have 3 times 10 to the negative first, now this is the same as 3 times 1 over 10, or 3/10. That would be in standard notation. In decimal form, though, which is also standard, it would be 0.3. So right, we have that 1 there, which tells us we have 1 0 to the left of the 3. 3 times 10 to the negative fourth means we'd have 4 zeros. This would be 3 times 1 over 10 times 1 over 10 times 1 over 10 times 1 over 10, or 3 times 1 over 10,000. And so you get 0.000, that's 4 zeros again from that 4 there, and then your 3. You have the tenths place, the hundredths place, the thousandths place, and the 10,000ths place, 3 10,000ths. All right, so that's hopefully enough to help you understand scientific notation, why we use it, and how to convert to it or from it. So the coefficient shows only the significant figures. All right, so here's just a table showing some example numbers in both standard and scientific notations. Figures. Here's some measured values, and again the numbers in standard or scientific. So volume of gasoline used in the United States each year. You could look at that, and you got to like figure out what is that. I don't know. It's the tens place. Okay, the thousands, the millions, the billions here, and so this is 550 billion liters of gasoline used each year. You could look at this too and see, okay, 5.5 times 10 to the 11th. Well, again, if we count them, there's going to be 11 place values there. Sometimes you'll get good at memorizing that this right there, 10 to the 9th, is a billion. So if I see 5.5 times 10 to the 11th, this is really 10 squared times 10 to the 9th. You have 100, and then that one is a billion, so you know it's 550 billion just from that. And it's honestly a lot easier because you don't have to count things when you've memorized that 10 to the 9th is a billion, 10 to the 6th is a million, 10 cubed is 1,000, and then 10 to the 12th I guess would be maybe the last one. That is a trillion. If memorizing those would help. Mass of a bacterium here now is a very small number. Like, look at that. You got to count all these zeros. There are 3, 6, 9, 12, 15, 18, 19 zeros. If you're, able to group them in the threes, you'll notice there's spaces between the zeros which help in there, but often that's not done that way. So you just end up counting them, which is time consuming, but you get 1 times 10 to the negative 19th kilograms. Now, 10 to the negative 12th would be a trillionth, 10 to the negative 15th would be a quadrillionth, 10 to the negative 18th is a quintillionth. So this is now going to the 10 to the negative 21st, which are a sextillionth. And so this is now 100 times larger. So this is 10 squared times 10 to the negative 21st equals 10 to the negative 19th. So this is on the scale of a 100th, or it's on the scale of 100 sextillionths of a kilogram, and so it's almost no mass. Significant. All right. Next, units. I talked about units a lot in class. These are things that we have to use in order to make sense of the numbers, right? We understand that, like, in America, we measure our weight in pounds. We can measure mass in kilograms, both kind of equaling some relation to how much of a material there is in something. We could measure the length of an object in inches or centimeters. We could measure the volume in ounces or milliliters or what have you. But again, a number by itself is just a meaningless abstract. You have to have some measurement to it for it to make sense scientifically. All right, and so when we're making measurements in whatever unit we're using, there's always going to be some level of uncertainty. And the reason is we're not God. Our measuring devices are imperfect. They have error. Always. All right, if you look at a ruler, there's all these little lines. For example, I have a ruler in front of me that obviously you can't see right now, but let me see if it'll, I don't know if it'll show for you when I do this, but there's all these lines. The ruler I have physically in front of me has both inches and metric system in centimeters. It's got 12 inches or 30 centimeters. The centimeters are broken down even further into millimeters. And in the first 10 centimeters, each millimeter is broken down further into halves of millimeters. And I'm telling you, being able to distinguish between millimeters is very difficult. You'd be very hard pressed to be able to figure out, is this closer to like 0.3 millimeters or 0.4? It's hard enough to see the half of a millimeter in between it. So there's always going to be error. no matter how much we were to zoom in, and also on the imperial side, they go to 64ths of an inch, which look even closer together than the half millimeters. We could zoom in with microscopes and spread that space out and measure the length of some microscopic object. But even then, even if you're looking at 100 times magnification, there's still something that's going to be even smaller. We still can't see atoms with any microscope. We're maybe just about to get there, or maybe we technically have. It's debatable at this point. But an atom might be on the scale of 10 to the negative 10th meters. That'd be 100 trillionths of a meter. It's so small, ridiculously small. So and that's basically the limit of what we think we'd ever be able to get to, because there's not much smaller than that. And in order to see something, you have to have something else smaller than it to shine through the microscope. So there's always going to be some error in our measurements, no matter what it is: length, time, temperature, weight, mass, whatever. And so you have to be aware of the fact that every measurement is somewhat erroneous. All right, but it can also be true that some measurements are better than others, even if you're trying to measure the same thing. And that's where the precision and accuracy come in. Precision is how closely multiple measurements are to each other. Closely multiple measurements align with each other. While accuracy is more how close a single measurement is to the true value. When I drive around in my car, I often look at the dashboard and see that there's a temperature that it's reading or measuring somewhere. Where the thermostat or the thermometer is that's actually measuring the ambient temperatures, I have no idea. But when I look at it, it might say right now outside it's, let's say, 52 degrees Fahrenheit. If I look at my phone or my watch with the weather app, it might say it's 55 degrees Fahrenheit in the city I'm in. Well, you should know that not every location, not every spot in a city is going to be exactly the same temperature. Temperature varies everywhere. It might be 20 feet away is completely different. And so there's some error. I often will look at it and see in my car, it says whatever the temperature is, and I compare it to the app on my phone or watch and see that there's a difference. Which one's accurate? Are either of them accurate? If I were to get a real calibrated thermometer and set it outside, would it match either of those two, the app or my car? Or would it be different than both? Because they're always different in my car. So that's tough. And again, the thermometer in the car depends, maybe there's engine temperatures that are changing it. Maybe it's, using a different methodology. It's just in a different location than the thing measuring temperature in the city I live in that's being reported to the weather app or whatever. So, there's that. And then you got to consider, is the thermometer I would be theoretically using also calibrated correctly. So accuracy is how close they are to the true value. If it says 55 on my app and 52 in the car, maybe it's more close to 53.5 degrees Fahrenheit. If I put the thermometer, it might say 54. It might say 53. Who knows? It could be the 55. It could be the 52 as well. At that point, we would know the accuracy of one of the thermometers when we have something else that has a known level of accuracy to its own self that's been calibrated. So accuracy is, again, a single measurement to comparing it to the true value. We could take a thermometer, put it in boiling water. You should know water boils at 100 degrees Celsius. If it's saying 98, then you know it's not very accurate. If it's saying 99, it's certainly more accurate. If it's 101, it would be as accurate or inaccurate as the one that says 99. It's just in the opposite side of 100. All right. If I put the same thermometer into 3 different samples of water that are boiling and it gives me the same value each time, then I know that that would be a precise tool to measure temperature, even if it's slightly inaccurate. So if I put it in one boiling water bath and it says it's 97, and another one it says it's 97, and then in a third one it says 97, I would know that it's precise, because the water should, those 3 samples of water, in the same room, should essentially boil at the same temperature. So I would kind of know from there, like, hey, if whatever it's reading, if it says it's 48, then maybe I should add 3 to it, make it 51. So being precise is important for your devices. If they're slightly inaccurate, it's not the end of the world as long as they're precise. Imprecise would be like if I'm getting 97 in one thing of boiling water, 96, and then 100, you're just kind of all over the place. Being imprecise is the worst thing. Again, accuracy is just one measurement. So we have this little image here kind of showing you the difference between accuracy and precision. On the left, we have accurate and precise. They're in the bullseye. In the middle, we have precise but not accurate. They're slightly, outside of the bullseye, but they're still clumped together. So that's, again, good. You could just correct for that error. And then finally, you have not accurate or inaccurate and imprecise. They're all over the board. And so that type of a tool would be useless. Notation. All right, the next topic is significant figures. Because our measurements are never going to be 100% accurate, unless you're counting something, I guess I should add that caveat to it. You can measure, I have 5 fingers on my hand, on my left hand. Counting that there's no error in that. We would call that an exact number. But for everything else where you're measuring using some standard measuring device, like a ruler, a graduated cylinder, a scale, whatever, there's always going to be some error. And we're going to be doing calculations. And when you're doing calculations, whether it's adding or subtracting or multiplying or dividing or logarithms or exponentials, there's going to be values, place values, digits that show up that really are beyond the scope of your knowledge. They'll show up on a calculator, but you have to understand that they're not actually numbers that you should utilize. The ones you can use we call significant figures. So significant figure is any number that is deemed to be appropriately defined and usable scientifically. And we're going to go over methods for determining how many significant figures are in a number. And that'll be in measured and in calculated values. All right. So a measured value is anything that uses a measuring device. Again, a ruler, a scale, a thermometer, a clock. All right. Those could be things that you're measuring. Exact numbers, on the other hand, are things that are counted. It could be counted or are known facts such as, you know, there's 12 inches in 1 foot. That is a fact. There's 100 centimeters in 1 meter. There's no doubt about that. Those are exact values. There's 60 seconds in a minute. So it only shows minutes in an hour. All right, so how to determine the number of significant figures? We have these 6 rules here you need to follow. First rule, all non-zero digits are always significant. So for example, I'm going to put the number of significant figures inside of parentheses for the numbers I'm about to write. So for the number 1, there's 1 significant figure. For the number 2, there's also 1 significant figure. They're non-zeros. If you have the number 11, this has 2 significant figures. If you have 135, that would have 3 significant figures. They're all non-zeros. That's rule 1. Any non-zero is automatically significant. You have 0 through 9 as possible digits, all right? And so in any place value. Zeros between non-zeros are also significant. So for example, if we have the number 101, this has 3 significant figures. If we have the number 10,004, this would have 5 significant figures, and so on and so forth. Actually, let me give you one more. Let's say, let me put semicolons here for making sense of that. Let's do 1,008,090. You have these zeros here. Oh, you know what? That was a bad choice. Let's not make it 90. Let's make it 92. You have those 2 zeros and that 0 there. They're each between non-zeros. These 2 are between the 1 and the 8. That one is between the 8 and the 9. So every number there is significant, and so you have 7 significant figures there. Leftmost zeros, rule 3 here, are not significant ever. They're unnecessary. All right, I'm 37 years old, but I would never say I'm 37 years old. That would be dumb. I don't need to tell you that I'm not 100 years old. I think you could look at me and make that assumption pretty easily. Hopefully, at least. Or that I'm not 10 feet tall. I'm 5'11". You know, I don't need to say I'm 0, 10s, and 5 feet 11 inches. So again, it's irrelevant to put those in front. Leftmost zeros are not significant. So something like 037 would only have 2 significant figures. Rule 4, rightmost zeros are significant if they come after a decimal point. So for example, if we have 1.0, the 0 is after the decimal, and it is rightmost, so that would have 2 significant figures. If we have 10.0, this actually is going to have 3 significant figures. Because there's a decimal there, like the number 10 could be 1 significant figure, all right? It could be 2 significant figures even, and I'll talk about that in a second. But 10.0 must have 3 because this 0 is after a decimal and to the right of the 1. And so that makes both of those zeros significant. All right, now, what about 0.1? Well, 0.1 has a leftmost 0, so this only has 1 significant figure. 0.01 also only has 1 significant figure because both of those zeros are leftmost. And so they don't matter, right? 0.1 is the same as saying 1 over 10. All right? We have a 1 there, one significant figure in that. And this is just for the place value, essentially. 0.01 is the same as saying 1 over 100. We still only have that 1 there to work with in fractional form. Now, if we say it's 0.010, this 0 is now significant because I bothered to write it in. All right, these are not because they're leftmost, but this is going to have two significant figures, those two there. Now, this is like saying it's actually, the tens place, the hundredths place, the thousandths place. This is like writing it as 10 1,000ths. And so instead of, it's equivalent to 1 over 100, but by putting in that 0, I'm telling you that it's significant. All right, and we could put we put 100 zeros after that 1. They would all be significant. The rightmost after a non-zero, after a decimal. To the right of a non-zero, to the right of a decimal, they are significant. If they're leftmost to the right of a decimal, they're not significant. If they're leftmost to the left of a decimal, not significant. Leftmost never are. Rule 5, if the zeros are rightmost and before the decimal, they may or may not be significant. So let's use the number 10. How many significant figures does that have? With no context, this has one significant figure. If I say there are 10 fingers on my hands, how many significant figures does that have? Well, that's going to follow Rule 6. When a value is absolute or exact, or has been determined by counting, it has an infinite number of significant figures. So that would be infinity. So the number 10 above had 1. If I have the 10 being the number of fingers on my hands in total, that would be infinitely many. There is no uncertainty in that count or measurement. Now, I could also say 10 could have 2 significant figures, but how? The reason this is only 1 significant figure is because we don't know anything about the ones place in that case. All right. It's a measurement, sure. All right, but is it going to be on the nines side? Like if I was measuring something and I rounded it, would it be on 9.9? Would it be 10.1? We don't really know where, officially lines up because uncertainty in your measuring device, for example. So you leave it off. You don't really know if that is significant. We've rounded it. It's been determined to be unknown, essentially. Sometimes, though, it can be rounded to 2 significant figures, all right? When that's the case, you put a decimal there. That tells you that that 0 is significant. All right, so the number 10 could have 1, 2, or infinitely many significant figures. Again, if we have 10, let's actually not do 10, let's do 100. This would have 1 significant figure. If we did 100 with a decimal, that would be 3 significant figures. If I say there's something like 100 centimeters equals 1 meter, the 100 centimeters would be infinitely many, and so would the 1 from infinity, or from 1 meter. It would also be infinity because that's an exact measurement, and it's an absolute fact. If you were to say you had the number 100, but it had 2 significant figures, you could not do that in standard notation. You would have to convert it to scientific, and you'd write 1.0 times 10 to the second. These are the only 2 significant figures. This tells you it is in the magnitude of the 100s place over here, and it has 2 sig figs. And that is another reason why scientific notation is important. All right, so that is the real benefit of scientific notation. All right, let me give you one more reason for significant figures. Another way of, right? So a significant figure could be, here, I'll just shorten it to sig figs, all right? A calculated value or a measured value. Cannot be more precise or accurate than the precision or accuracy of the device used to make a measurement. Simply put, you can't just invent numbers, all right? I've got a ruler in front of me. Again, it goes in the centimeters, down to millimeters, down to halves of millimeters. If I were to measure the thickness of a sheet of paper, on the thinnest dimension of it, it would be certainly less than half of a millimeter. But could I say that it's like 359 micrometers? Is that the thickness of this sheet of paper I have in front of me? I have no idea. It is impossible for me to know by using this ruler. I would be completely inventing that. This is 3.59 times 10 to the negative fourth meters, because 1 micrometer is 1 times 10 to the negative 6 meters, and we have 359 of those, so the negative 6 becomes a negative 4. It's bigger by a factor of 100, or 10 squared. All right, it is just too small for me to measure. Now, if I'm putting it in centimeters, this value here would be 3.59 times 10 to the negative second centimeters, right? If I'm putting it in millimeters, it'd be 3.59 times 10 to the negative first millimeters, or 0.359 millimeters, right? Maybe I could look at it, and I just made up the number, but if I'm looking at it, it's really hard. I can't. Is it almost 4/10 of a millimeter? I have no idea. But I'd be making it up. Maybe this right here would be what we'd call a measured value, which, by the way, I was just looking at it, it's definitely thinner than that. But the other two here would be estimated values. Every measurement will have one that you can say is for sure, or a known value, and the other are going to be estimated values. Always. Okay. You could keep the 3. Like if I'm using this ruler, I would keep the 3 because the next value is a 5. It would round up to 4 times 10 to the negative first millimeters. That's actually how we would measure that. All right. In that way, we know, well, I don't know anything about the hundredths of a millimeter, let alone the thousandths of a millimeter. But I can go in between a single millimeter and make estimates with it that are reasonably close. If I was to redo it, I'd probably say it's 0.1 something. I might say it's more like 1 times 10 to the negative first millimeters for the thickness of the sheet of paper. But anything beyond that would just be complete speculation. We just don't have that information. So it can't be more accurate, and it can't be more precise than the thing we're using. Now, if I put the piece of paper under a microscope that was able to look at it in 3 dimensions at much finer, details, much closer together, great graduations of a line using to measure it, because you can get 1,000-time magnification on some microscopes that we have. And so, a millimeter would look as long as a meter, so you could measure down to nearly a nanometer, essentially, in some microscopes. And, it should be possible then, but that would be using a better tool than just the ruler I have in front of me. All right, so that is why we use significant figures, defining it. The next thing will be just here's some numbers, how many sig figs are in each. The number 123 meters has 3 significant figures. They're all non-zeros. 40,506 millimeters has 5 significant figures. These zeros are in between non-zeros, so they are significant. In 9.800 times 10 to the 4th meters, I need to re-emphasize that we do not include this in significant figures, but in scientific notation, the coefficient there tells you how many. There's 9, 8, and then 2 zeros, so this has 4 significant figures. All right. 22 meter sticks. This is kind of a trick, but it has infinitely many because you'd be counting those 22 meter sticks. 0.07080. These are leftmost, so they don't count. These are rightmost after a decimal, after a non-zero, so those are all significant zeros there, and therefore that has 4 sig figs. And then 98,000 meters. We don't know anything about those 3, so we can't assume they're significant. So this has 2 sig figs. Mind you, this value, 9.8 times 10 to the 4th, actually is 98,000, but we were saying that those 4 were significant, whereas here it's only the 9 and the 8. We had more information to go with here, maybe a better measuring device, maybe it came from a calculation that had other stuff that told us it was 4 sig figs, but they're the same number, just with different sig figs. All right, so rounding, I mentioned a bit ago, you're going to round to the correct number of significant figures based on the measurements you start with. So let's say we measured something that really was only able to measure to 4 significant figures. We would look at the 1st, 2nd, 3rd, 4th, and then the 5th, and we see that's a 2. For the next one, we see round to 4. These are not significant, so you ignore those, and you have 1, 2, and then we're going to look at the 3rd one. Here, 2 again, 1, 2, 3. Then that one's going to be the 3 sig figs, 1, 2, 3, and then 4. And the final one, 3 sig figs, 1, 2, 3, and then 4. The way we round it, now we have any number between 0 and 4, you'll round down. Any number 5 to 9, you'll round up. Since the first one has a 2 that I've boxed in, you're going to round down. So this becomes 314.7. Now, the standard way you're probably used to rounding would be to put those as zeros. Right, we're rounding the 5th and 6th place values down to 0. But this still has 6 significant figures. So when you're rounding in the decimal portion, you have to just erase those off. And so 314.721 meters rounded to 4 sig figs would be 314.7 meters. 0.001775 meters rounded to 2 sig figs is going to be 0.001, and we have a 7 there boxed in, so that makes them round up to 8. Again, it would be 00, but we're not going to do that because then they would be considered significant, which would undermine the purpose of the rounding anyway, so you get 0.0018 meters. For the 3rd number, you have 8792. The 9 causes it to round up, so it becomes 8,800 meters. All right. Now, we do keep the zeros in, because they're in the whole number place values. They're not in the decimals like the previous two examples. If we rounded it to, if we took off the zeros, it would be 88 meters, and 8,792 is clearly not anywhere near 88 meters. 87.073 meters has the 7 boxed in, so that's going to cause this to round up. You get 87.100 meters. Again, those two zeros are in the decimal places, so you don't include them. It's 87.1. And then finally, this 9 boxed in is going to cause that to round up to 9,010. Because this is a whole number, the decimal would be right there. The decimal could be right there. All right, you have to keep the 0 here. If you put a decimal in, then that would have 4 sig figs like we started with, and that would be wrong, so leave it off. And now that has 3 sig figs and is correct. Now we're going to talk about calculations. We have, I would say, 3 types of calculations we'll do throughout this course and subsequent courses. You'll have addition and subtraction being one of them, multiplying and dividing will be the second, and then logarithms and exponents will be the third. The rules for adding and subtracting will be the same because they're the same level of hierarchy of operations in mathematical calculations. The answer to a simple addition or subtraction problem, or a step in a series of calculations, is to be rounded to the same number of decimal places, not digits. You're only looking at decimal places as the measurement with the fewest number of decimal places. Seems kind of weird. We just talked about how to determine sig figs, but now we're only looking at decimal places. I didn't create the rules. That's just how it is. Follow the rules. So we have these numbers here, 12.52 plus 349.0 plus 8.24 meters. All right, so we pull out a calculator. Well, we'll just do it by hand, I guess. 12.52 plus 349.0 plus 8.24, you'd get 6, 7 decimal, 19, right? 4, 5, 6. You get 369.76 meters. Your calculator would show you that. But this is in a science class. These would be lengths that you would have measured with a ruler. Now, it turns out that, this is a ruler, a measuring stick that would be, let's say, 20 meters. The next one, maybe that one is 10 meters, or maybe it's the same one that goes to 20 meters. But this one is clearly 349 meters. That's probably, let's say, a kilometer measuring stick of some sort. It's not going to be the same. You'll notice these have 2 decimal places, while the middle one only has 1. Even though it has 4 significant figures, which is tied for the most sig figs in those, it has the greatest bit of uncertainty in the hundreds place because it doesn't have that there. So if we used this value, that would be saying we do know that it's 349.00. We in fact don't know it's a 0 there. So numbers that could round to 349.0 using the second decimal point will be 349.04 all the way down to 348.95. Right? This is the hundredths place, that's the hundredths place. This would round down to, that many, right? It would round down. And this would cause the number to round up. So if I'm writing it in a more logical way, 348.95 to 349.04 is a range of error there. We just don't know. if I had 348.95 instead, plus 12.52 plus 8.24. We have 7, 11, 10, 15, 17, 10, 18, 19, 5, 6, 3. So it's 369.71. It does not equal the 6 there. And that's why we can't use that last place value from the 349 or any of those measurements. We just don't know. If it was 349.04 plus 12.52 plus 8.24, it'd be 369.80. Again, it does not match this. So the true answer is that it's 369 point, because we got that from a calculator and it's a 6, we round it up. It's around there. Okay, that's the best we can do. And don't forget your units would be in meters. The same rules are going to be followed for subtractions. Again, an addition is adding things together. Subtraction is the opposite, obviously, you're removing. But they're addition and subtraction inverse operators. So for example, if I give you a problem like 3 plus 4 minus 4, I have a plus 4 and a minus 4 sequentially, so this is just 3. They've undone each other because they have the same value and opposite operators. All right, next, the rules for multiplication and division will both be the same. Multiplication is repeated addition and division is repeated subtraction, as it turns out. So it's kind of funny how they differ in their rules, but either way, we follow different rules. I didn't create them. The answer to a problem or a step in a series of calculations is to be rounded to the same number of significant figures as the measurement with the fewest number of significant figures. The position of the decimal point has nothing to do with the rounding process when multiplying and dividing measurements. So for example, let me show why they can be different. Again, if I take the numbers, let's say 8.4 plus 2.95. You get 11.35. You would round this to 11.3. Actually, let's just eliminate that. And no, we'll go one more. 2, 3, 4, something like that. All right, 4, 5, 3, 5. So there we go. So we have 8.42 plus 2.934. That adds up to 11.354. We go from 3 significant figures and 4 significant figures in the numbers shown to what has 5. Well, when we're rounding it, because we're actually using the one with the fewest decimal places, which is 8.42 having 2 decimal places, so really this should be 2 and 3, while this has 3, we need to round it to 2. So this 4 rounds down, so it becomes 11.35. This now has 4 significant figures or 2 decimal places, which matches the 8.42. Another reason for addition and subtraction why to do it this way is, like, when you're measuring something, you know it's like a full inch or a full centimeter, and then the last parts, because they're so close together, that's where your estimations come into play. And so you can think of it that way. And then you're adding or subtracting, and you can change to having more place values in front or less. So here we had 8 and 2, went up to the tens place value. All right, so we went, we added one over here. If I had 8.420 and then 2.934, adding those together, you would get 11.354. And then you would go from 4 sig figs and 4 sig figs to 5 sig figs, and it would look bad. And so you'd round it to 11.35, say, well, that has 4. But in fact, that's wrong, and this is right. All right, we have enough information to say we do know that's a 0 and a 4 there, even if they're estimated themselves. And it just so happens that they add together to create a new place value in front. With subtraction, you could take away like 101.4 minus 2.8 gives you 14.6. Well, okay, we're going to take a 10 away from there. All right, well, 100 minus 2 is 98.6. All right, for this answer there. And so we lost a place value. We had the hundreds place, now we don't, right? And that's just what it is. So these are just known. We're only like saying the tenths, the decimal points are unknown. For multiplying and dividing, it's different though. So actually, let me do one more thing. We have 8.42, right, plus 2.934. That came out to 11.354. If I change the decimal point to make this 84.2 plus 2.934, you'll see that we get a completely different number, 4378, 87.134. Sure, fine, the last number is the same, but the rest of it is different. And that's generally going to be true for adding and subtracting. If you change the magnitude when you're adding, you're going to get different sums. Multiplying and dividing, now if I take 13 times 5, I'm going to get 65. But if I take 1.3 and I multiply it by 5, I get 6.5. If I take 13 times 50, I'm going to get 650. You're getting the same thing repeated no matter what. If I make it 1.3 times 50, I'm actually going to get 65. All right, so you're always getting it. You're moving the decimals. The decimal point doesn't matter in multiplying or dividing. It only matters in adding and subtracting. So, turns out we can use the entire number for multiplying and dividing. So the answer to a problem is to be rounded to the same number of significant figures as the measurement with the fewest number of significant figures. The least precise and accurate measurement, essentially. The position of the decimal point has nothing to do with the rounding process when multiplying and dividing measurements. All right. I'm also going to put here and logs and exponential notation. They're going to follow this as well. Logarithms are repeated divisions and exponential are repeated multiplications. So let me just give you an example. If I say 10 cubed, this is 10 times 10 times 10. If I say 3 to the 4th, this is 3 times 3 times 3 times 3. You're just repeating that multiplication. So that's why they follow the same rules as multiplying and dividing. All right, so here's some examples of multiplication and division problems, rules for significant figures. 7.55 times 0.34. We have 3 sig figs to 2, so your answer has to be to 2 significant figures. Okay, so this will come out on your calculator to 2.567, which has 4 numbers shown, but we're rounding it to 2. So 1, 2, and then you have a 6, so that's going to round up, and that makes it 2.6. The next thing you do have to consider for multiplying and dividing, though, are what the units are. Meters times meters will be meters squared. So 2.6 square meters would be the answer there. In the next one, you have 2.10 with 3 sig figs, 0.70 with 2 sig figs. So the answer will be to 2 significant figures. And you do that calculation, and you get 1.47. Again, you have meters times meters, so square meters. But we have 2 significant figures that we're supposed to round to, not 3. And so this becomes 1.5 square meters, because the 7 rounds the 4 up to a 5. And then finally, the third one is a division. 2.4526 has 5 significant figures divided by 8.4, which has only 2. So the answer is going to be to 2 sig figs. 2.4526 divided by 8.4 on my calculator comes out to 0.2919761905. And then the units, you have a meter divided by nothing. So it's actually going to stay as a meter. You could say it's 2.4526 meters divided by 8.4 meters to the 0, and say that's meters to the first. Meters to the first divided by meters to the 0 power. I know using letters and stuff sucks in math, but it's not following any different rules. When you have division of the same base here, in this case meters, becomes 1, or m to the power of 1 minus 0, which is m to the first, which we can say is just meters. The same is true if I have 3, let's say 3 divided by 0, right? No, don't want to do that. 3 divided by 1, I could actually say this is 3 to the first divided by 3 to the 0, which is 3 to the 1 minus 0, or 3 to the first, which is just 3, which is why any number divided by 1 is itself. All right, so we get that. Now, the next thing you might think about is, how do you take 2.4 meters and divide it 8.4 times if division is repeated subtraction? What you can do is move the decimal point to the right once for each. You're essentially multiplying by 10, and then it becomes 24.526 meters divided by 84. So now you could logically think that you could split some measurement of 24 meters or so up 84 equal times. But again, it doesn't matter whether you're moving the decimal or not, you're going to get the same numbers. 2.4526 divided by 8.4 will give you the same value as 24.526 divided by 84. And that's this value, 0.2919761905. But again, we're going to round that to 2 significant figures. We have 1, 2. Remember, the 0 is leftmost, so not. We have a 1 here, so this will round to 0.29 meters. All right, so this slide got messed up in the conversion into the app that I'm using. Normally, I have to convert my PowerPoint slides to PDFs to work in here, and I guess during that conversion, this slide got messed up. So sorry for the way it looks. But Section 8 is solving chemical problems, and what we're learning here is dimensional analyses. So if you can see it over here, it says these are used to convert one set of units to another. Like I said, I'm 5 feet 11 inches. If you wanted to know how tall that is in the metric system, you need to convert it to centimeters or meters, however, whatever works for you, or even millimeters or micrometers. I mean, it could be whatever. But I have to do something to make that conversion. And this probably should not even be there. That would be from a different book, so ignore that. But we use unit factors or conversion factors in order to convert from one set of measurement in one set of units to another. When two measurements are equal in value but expressed in different units, a division of the two would equal 1. Theoretically, like 1 inch is equal to 2.54 centimeters. That is an exact conversion. The imperial system of length is actually defined based on the metric system. So that was done a couple years ago in America. You just didn't know about it. Like when I was growing up, this was some near enough to be usable value. Maybe it was 2.54 or 2.535 or something. They rounded it to 2.54 and said, now that's exact. So this actually has infinitely many sig figs for both of those. If I take a measurement, well, if I take an object that has been measured to be exactly 1 inch and another object that's been measured to be exactly 2.54 centimeters, they would be the exact same length. So they're called unit factors because these are the same lengths. That length divided by that length is 1. You'd have exactly one. Let's say I have paper clips that are 1 inch and another paper clip 2.54 centimeters, and I measure, I would need one paper clip for making that same length. So they call those unit factors or conversion factors. Unit factors are used to convert from one unit to another, since by definition the two measurements, although different in units, are equal in value. So for example, a pencil is 7 inches long. What is this length in centimeters? Well, again, 1 inch is 2.54 centimeters. What we're going to do in these problems is what I call the box method, or what is more appropriately called the factor label method. All right, so I'm going to take the measured value, 7 inches. Always find the measured value, okay? Every question we have, if it's math-based, find out what's been measured, write that down, 7 inches, 7.00 inches. Then you're going to write a line, a horizontal line, like this. And then you're going to make a vertical line like that. This is why it's called the box method. You're kind of building these boxes. The vertical line represents multiplication. The horizontal line represents division or a fraction bar. All right. In the measurement 7 inches, the number and the units belong in the numerator of a fraction. I could say it's 7.00 inches per pencil, essentially. Okay, but that would be the number 1. If you're going from words to expression in numbers, the fraction bar could be read as the word per or over, whatever. Because it just says 7 inches long, we don't need to put anything down here. But I want you to remember that it is like 1. But when you're multiplying, as we'll see from left to right, you're multiplying by 1 doesn't change anything. The next thing we're going to do is put in the conversion factor. So first things first, we have our measured value in the top left corner. Next, we're going to have the conversion factor. All right. And that is the 1 inch equals 2.54 centimeters. Focus in on the units. The numbers are almost irrelevant. These units, inches to centimeters, we're trying to measure it in centimeters. So that has to end up here, and the inches have to end up down there. And it was 1 inch is 2.54 centimeters. Now again, you're multiplying and dividing here. These inches are going to cancel out. If I say 3 times 4 divided by, let's, I guess, put 1 times 3, I could write it as 3 times 4 over 3 and simply say those cancel out and you get 4. I could write it also as 12 over 3, and 12 divided by 3 is also 4. So same thing works for the units. The inches are going to cancel out there, and now you've got it 7 inches converted into centimeters. So 7 times 2.54, we have 3 sig figs, we have 3 sig figs, actually, I'm sorry, not 3. We have infinitely many, and this is also infinite if you're even going to include it. So this comes out to 17.78 centimeters, and the least, the number with the fewest, I should say, sig figs is 7.00. So 1, 2, 3, we have an 8 there. This rounds up to 17.8 centimeters. Question number 2. A student has entered a 10-kilometer run. How long is this run in miles? So we have a 10-kilometer run. That would be the measured value, and we're converting it to miles. Now, you could find a conversion table that has the value. I'm going to do the full thing. Actually, let's use the conversion. 1 mile equals 1.61 kilometers. So we have our measured value of 10.0 kilometers, and we're trying to get rid of kilometers, so put that in the denominator. We're trying to finish up in miles, so 1 mile right there. Kilometers cancels out, and you get from this 10 divided by 1.61, and that's going to equal 6.211180124 miles. Great. Let's do the exact thing, because we can act this had 3 sig figs if we rounded it. Let's say these were infinitely many, all right, but that's got error. But it also, I have it as 3 sig figs, so we could round it to 3 in a sense, and so it would be 6.21 miles. If you're running a 10K, it's about 6.21 miles. If we do the full thing without any error, 10 kilometers, you would have to say this is equal to 1 kilometer is 1,000 meters. 1 meter is 100 centimeters. 2.54 centimeters is 1 inch. 12 inches is 1 foot. And 5,280 feet is 1 mile. All of these are infinitely many sig figs. All the units cancel out, leaving us with miles, except this has a measured value with 3 sig figs. So we get 10.0 times 1,000 times 100 divided by 2.54 times 12 times 5,280. All right, so 10 times 1,000 times 100 divided by 2.54 divided by 12 divided by 5,280. This comes out to 6.213711922 miles. Now, rounding it to 3 sig figs, 1, 2, 3, we have a 3 there. It's also 6.21 miles. So that's great. But technically, if you measured it at 6.21 miles, you'd be off. All right, so if I multiply that by 5,280, it's 32,808.39895 feet. That 10K. Whereas 6.21 times that is 32,788.8 feet, for a difference of 19.59895 feet, or 19 feet and about 7.2 inches. So if you ran a 10K and they really were measuring it in miles at 6.21, you'd be off by 19 feet. Now that may not really matter, it's only like a second of running or two, but if there's world records involved, then that would matter. All right, question 3. The speed limit on I-20 is posted as 70 miles per hour. How fast is this in kilometers per hour? So 70 miles per hour is how I would write it. And we're converting it to kilometers per hour. Because it said per hour, we have the 1 here and the unit hours in the denominator. We could just use the same thing we had before, right? 1 mile is 1.6 kilometers. And now you have it in kilometers per hour. So 70 times 1.61 divided by 1 is 112.7 kilometers per hour. Roughly speaking, 113 kilometers per hour. Keep in mind, if it's a speed limit, this actually has infinitely many. That would be infinite. If we did the full thing, by the way, 70 miles per hour times 5280, that'd be feet, times 12 inches, times 2.54 centimeters, divided by 100 centimeters per meter, divided by 1,000. It's actually the true value, 112.65408 kilometers per hour. And using infinitely many significant figures, this would actually be the answer, because that's what the calculator gives. But, you know, they're not going to worry about that in Canada or places that use both metric and imperial for speeds. So 113 would be enough. And they'd probably round it down in their books to 110. So they're, you know, what we would say is 70 miles per hour, they'd probably post it as like 110, just for simplicity. All right, and then finally, if there are 365 days in a year, how many seconds are in a year? So we have 365 days per year. All right. Well, we have 20, that's going to go up here, 24 hours in one day. So days cancel out. We have 60 minutes in 1 hour, so hours cancel out. And we have 60 seconds per minute. So minutes cancel out. Now we have seconds per year. So 365 times 24 times 60 times 60. This comes out to 31,536,000 seconds per year. To put that into perspective, you know, every year you're gaining 31.5 million seconds, give or take, right? If you take 1 billion seconds and you divide it by 31,536,000 seconds per year, those cancel out. And that tells you how many years it takes to equal 1 billion seconds. And that would be 31.7 years to be 1 billion seconds old. I have reached my 1 billion second year old, or whatever, second old life. If you have, welcome to the club, or when you do, welcome to the club. Now, the reality is nobody's going to reach 4 billion seconds. If you're 95 years, a little bit older than that, you'd reach 3 billion seconds. So if somebody ever asks, how high can you count? It's probably at most 3 billion, because it's going to take longer than 1 second to say most numbers. So there is a limit to how much you can count. All right, and the last slide here is solving these chemical problems, converting from one unit to another again. These are actually probably easier than the previous, but whatever. So we have 15 cubic centimeters to liters. One thing you need to understand about this is that 1 cubic centimeter is equal to 1 milliliter. So I could first just say this is 15 milliliters and converting that to liters. Well, let's do it the proper mathematical way. Our measured values 15 cubic centimeters, and 1 cubic centimeter is 1 milliliter, so those cancel out. And now there's 1,000 milliliters per liter. Milliliters cancel out. So we're ultimately just dividing 15 by 1,000, and so this is 0.015 liters. We had 2 sig figs from there. We have 2 sig figs here, and so there's your answer. For the next one, 7.38 grams to kilograms. Again, our measured value is 7.38. Going to kilograms, you have 1,000 grams per kilogram. Grams cancel out. And so now we get 0.00738 kilograms. Just to show you, the decimal would be here. Dividing by 1,000 moves the decimal to the left 3 times. All right, so you have 1, 2, 3. And then you have a 0 there, and then you put a 0 there because that's where the decimal goes. So, and I apologize. For whatever reason, I don't know if it's the Apple Pencil, my iPad, or this app. Sometimes it screws up and it just writes a whole bajillion things all over the screen at once that I have no control over. And I'm not going to spend the time redoing these edits, but it's 0.015. For this, you have 1, 2, 3 times you move it over, 1, 2, and then a third 0. Again, you're dividing by something with 3 zeros, so you just put 3 to the left. And so that's how you get those. You should be able to do that in your head pretty quickly. Next one, 6.7 seconds to milliseconds. Starting off with seconds, you have 1 second is 1,000 milliseconds. Seconds cancel. And now 6 times 1,000 is 6,000. 0.7 thousandths would be 700, so 6,700 milliseconds. So here you're adding 3 to the right. Let me do that. 6.7. 1, 2, 3. Those go there. The decimal would go there, but we are not including that. It doesn't matter. It's just 6,700. But again, there's 3 place values we're multiplying by from those 3 zeros, and we've got 3 there after the 6 before the decimal now. So the first 2 were going from small units to large. We divided. This third one is from a larger unit, seconds, to a smaller unit, millisecond, and so we multiplied. In D, 94.5 grams to micrograms. What we're doing here is you need to know the conversion, that 1 million micrograms in 1 gram. So grams will cancel out. Standard notation will just give you a really ridiculously large number. So you could change this to 10 to the 6th micrograms, all right? And then you get 94.5 times 10 to the 6th micrograms. But this is not a proper standard scientific notation, so you have to move that over. See, there we go with the pen. And so this is 9. If we just take the 94.5, this is 9.45 times 10 to the 1st times 10 to the 6th. Now these combine together to give you 9.45 times 10 to the 1 plus 6. It's rules of exponents. So this is 9.45 times 10 to the 7th micrograms. All right. Now in E, 0.073 centimeters to micrometers. Erase that. Our measured value is 0.073 centimeters. It's going really bad. All right, there we go. Now, I don't have the table here to show right away, but you have 100 centimeters is a meter. I could also write that as 10 squared centimeters equals 1 meter. Again, 1,000,000 micrometers. And for whatever reason, the longer I go in these videos and what have you, the more this stuff messes up. But 1,000,000 micrometers is also equal to a meter. 10 to the 6th micrometers is 1 meter. What you want to notice here is the difference in those. They're off by 10 to the 4th. So it turns out it'll be 10 to the 4th micrometers is equal to 1 centimeter. When you're combining, you can go to the base value and back from centimeters to meters and then meters to micrometers, or do something like this and get it directly. So in doing the calculation, you get 1 centimeter for 10 to the 4th micrometers, or that's 10,000 micrometers per centimeter. Now, we have our decimal place here, and we can move it 4 times, or realize that there's 3 to the right of it, and we need 4, so we're just going to add a 0 in there, and the decimal has moved, so it becomes 730 micrometers. 1, 2, 3, and finishing off with that 4. Again, we don't need the leftmost, they're insignificant, so it's just 730 micrometers. Now the last one is going to be the most challenging, and that would be because we have grams converting into kilograms, and we have cubic centimeters converting into cubic meters. The next, also it's cubed there, so that's critically important. So your measured value is 7.21 grams per cubic centimeter. The first thing that I'm going to do is convert it to kilograms. So 1,000 grams is 1 kilogram. And I could write it also down here like 10 to the 3rd grams per kilogram, or grams. I'll do both. All right. Then we have to do cubic centimeters to cubic meters. Well, again, 100 centimeters is 1 meter. If I put in 100 centimeters per meter, well, that actually is only going to cancel this out to make it square centimeters. So you need to do it a 3rd time. Oops, didn't want to make that swooped. So that centimeter cancels out the square to make them centimeters to the 1st. So you have to do this a 3rd time, and then that will cancel out this. And now, when the grams cancel out, you get kilograms per these multiplying together to be cubic meters. So a quicker way to do it would just be to realize that it's cubed, and so cube that all in front, cube that. You get 100 centimeters cubed, or 100 cubed centimeters cubed is 1 cubed meters cubed, and 100 cubed is 1,000,000, because I'm just going to write this as 10 squared cubed cubic centimeters, and 1 cubed is 1, so you get that. Another rule of exponents is when you exponentiate an exponential, you multiply those values together. 2 times 3 is 6, so 10 to the 6th cubic meters is 1 10 to the 6th cubic centimeters is 1 cubic meter. All right, we have 2 zeros, and we're doing it 3 times. 2 times 3 is 6, so you end up with 1,000,000. 1, 2, 3, 4, 5, 6 cubic centimeters is 1 cubic meter. All right, so you have to do that 3 times. Now over here, because we have 1,000,000, I'm going to write it as 10 to the 6th cubic centimeters is 1 cubic meter, just to make this the simplest way. So 10 to the 6th cubic centimeters is 1 cubic meter. The cubic centimeters cancel out, and again, kilograms per cubic meter. But because I did this in exponential, you can see there's a 10 to the 6th divided by 10 to the 3rd. Another rule of exponents is when you're dividing the same base, the exponents subtract. So that comes out to 10 to the 3rd right here while that gets eliminated. So it ends up being 7.21 times 10 to the 3rd kilograms per cubic meter, and you're done. In scientific notation, or 7,210 kilograms per cubic meter. You have to remember to use that unit as many times as it is taken to the power of. If it's 2, you do it twice, or square it. If it's 3, you cube it, and so on and so forth. All right, and that is it for this lesson, and that is it for chapter 1.